Okay, so I want to take a little time to start talking about some atomic absorption background in preparation for the lab starting next week. Okay, maybe half an hour on that. I want to take a break then when we're done with that and then talk a little about lab 2. There's a couple things that I want to point out. One is most of you had the lab 1 reports returned, and I'll finish the rest of it today and it goes back to you. I think what I want to do today is from say about 12:30 to 1:30. People want to come by and talk about any questions with the lab 2 report. I'll be available to do that. Does that work for people? So it'll be right near my office in the Physical Sciences building, 12:30 to 1:30 today in class. You can come ask questions about that. The Van Deemter, we think we figured out why it wasn't working well in the Monday-Wednesday section. What it appears what is happening is that as the flow rate was being changed, the recommended optimal current in milliamps to the suppressor wasn't being changed. And so what was happening is that the current to the suppressor, which sets essentially the potential at the cathode and the anode where you're oxidizing water or whatever, that it wasn't the optimal setting, so you were probably over-oxidizing because the current was too high. As you lower the flow rate, the current should have changed too, because you have a scenario where you have the eluent flowing through and water is being oxidized here to generate the hydroxide and the protons, and those are diffusing into the eluent mobile phase space. Okay? And if the potential here is too high, you're over-oxidizing this and generating too much protons, and then essentially what you're doing, you're over-suppressing. So as this flow rate would decline, and this would not change, and you could lower it appropriately, then the residence time of the fluid in the space suppressor will increase because the flow rate is reduced, right? And so what you're doing is you're having a higher concentration of protons that are diffusing into the eluent space because it has a longer residence time in the suppressor because the flow rate's lower, and we're over-suppressing. And so many of you recall that you would see these baselines going and diving down and getting really negative, right? And it's because of that, I think, right? Now the double peak that the people were getting in the Monday-Wednesday section, I still don't know what that's all about. The concentration was too high. What we've done though is that in the Tuesday-Thursday section, they were able to generate chromatograms. I think they used fluoride, not chloride, because fluoride comes out sooner than chloride, so it's a bit faster. And they were getting reasonable peak shapes. That section was kind enough to share, and Taylor shared those 4 or 5 chromatograms and the data from the instrument minus the plate height, which you can calculate. And I posted that on the web. And so everybody can share and use that same data set in attempting to construct a Van Deemter plot, which is the plate height versus the mobile phase velocity, right, for your lab 2 report. Is that clear? So it's on the website.
How do we change the current though? Were we supposed to change it manually, or that's the instrument job?
Apparently. You're supposed to change it manually.
So we do change the flow rate,
Yes.
and then you go back and change the current.
Well, when you set the method for the different flow rates,
Right.
apparently there's a window that tells you the recommended current for the suppressor that needs to get entered into that space, into that little window for the suppressor, and it was staying at 6 millivolt or 6 milliamps or whatever, and apparently should have been lowered. Right?
Nice.
And we've always known that having a suppressor generated a Van Deemter plot with an ion chromatography fitted with a suppressor is always challenging because you have that effect of the suppressor that's greatly influencing this process as the flow rate changes, right? And so it's a bit of a confounder, but we've had success in the past, but big success. Guaranteed success.
My understanding from what Taylor said was that a Van Deemter plot was just a linear line instead of going back up in
In a deflection?
the width or the area. Deflection.
Well, Well,
There was no inflection point.
You're looking for something that's kind of going like this with no phase velocity and plate height.
All right, so
right?
the play height, I guess, like, didn't go back up.
That's right. So I think what you may have is something that looks kind of like that, right?
So that doesn't really tell us enough, does it?
Well, it doesn't tell us where the optimal is, but you may look at how if this is a straight function or a straight function that's starting to show a little bit of inflection at the bottom to get a sense of that, right?
But if it's straight, we can't tell.
That's right. If it's straight, you can't determine what the optimal flow rate is
Okay.
based on the separation, right? Because you're up here at 1.2 mils per minute, and you would say, clearly that's not optimal because we have a greater a smaller plate height, which we would interpret as a greater sort of resolution potential in the column if we have a lower flow rate. And why didn't you use a lower flow rate?
Didn't make time.
Well, that's one. You didn't have enough time, but I mean, because it's a trade-off between time and performance. And were you adequately separating all the anions in your sample? Yes, all right. And so you would, as an analyst, you would say, why go slower and analyze half the number of samples in a given amount of time if I don't need to because I have adequate resolution with the samples that I'm analyzing? Right? And you might say, oh, why not go to like 2 mils a minute and I'll be out of here in half an hour, you know? And then you say, oh, the pressure's too high, the column starts to leak, or whatever. Okay. So the data are on the website, and if you have any problems with those, because you know those chromatograms, the font size is so tiny, they're pictures, you got to blow it up to really read it, right? But you're going to have to use those chromatograms to measure the parameters of the peak, right? To calculate the plate height. Okay. Because he did not give you the plate height of what he said. He deleted that part. Okay. So that's that. Still, when we finish, we'll talk a little bit about Lab 2, but if everybody's available to come by here, then I can postpone this. If not everybody's available, then I'll talk a little bit about Lab 2 and go over some things that I want to reiterate to people before we do the quiz. And we'll just do the quiz at the end, stop like 15 minutes before we get started. Okay. So, for some reason, it's not double projecting, so I guess we'll just okay, we don't have to. So, we're going to talk about this before. We talked plenty about this in the introduction about why analytical accuracy matters. Right, we did all this. Now, let's talk about atomic spectroscopy. So I made the point last time of saying we're sort of evolving now from going from methodologies that are based on assessment of things at the molecular level. You know, the ion chromatography is sort of a combination of atoms and molecules. And now we're going to move into atomic spectroscopy, and this is going to lead us into mass spectroscopy. We're looking at species at the atomic, and we'll talk a little bit about molecular mass spectrometry later on too. And so atomic spectroscopy means what? What does that tell us right there, based on that simple name?
Atom composition.
We're looking at atoms, right? Not so much atom composition, but we're detecting things based on what atoms do. And so, of these 3 categories of instrumentation, atomic absorption, what's happening?
Detecting the atoms, I guess.
What?
Detecting the atoms, using the binding rules.
Okay, what's happening? Well,
Atoms are absorbing energy and then giving off
okay,
energy.
we don't care about that part, right? Okay. That's why they call it atomic absorption. All we care about is the property that atoms are absorbing energy in the form of photons. Okay. And it's that absorption, just like we measured in UV vis spectroscopy, we're measuring absorption, right? A molecule, in this case it's atoms. And next one I have what the approximate working rate range is, or detection limits, depending on the element that's being looked at, that's being analyzed. And they're in the, the very low to high microgram per mil range, right? And this is, it depends on the kind of atomic absorption. So the one that you have in the lab that you're going to use is what's referred to as a flame atomic absorption. And a flame is because it's going to have an air-acetylene flame like a welding torch. It's going to come out of the instrument, and your sample is going to be aspirated into that hot flame. It's about 2,000 to 3,000 degrees Kelvin. And it's going to take that liquid sample that you introduce, and it's going to desolvate it, and it's going to vaporize it, and then it's going to atomize it. And then the atoms will be their free state in the gas phase for a very short amount of time, and then they're going to absorb light that you are passing through the flame, just like you would do with UV vis, except it's we prepare the instrument processes our sample differently. There's other kinds of atomic absorption spectrometers that have a much higher detection limit, much better detection limit than this. We'll talk a little bit about that too. So then atomic emission, what's that?
Atoms release energy.
Okay, in the form of?
Photons.
Photons? Photons, right. Okay, so they are emitting photons that we are measuring, right? And many of you will have a demonstration of some of the mass spectrometer facility and the atomic ICP, atomic optical emission spectroscopy facility in the Earth and Marine Sciences building. And some of you will choose to use the atomic emission spectrometer to do your independent study project. Right? And in that case, we have the advantage of, unlike atomic absorption that can measure one atom at a time, one element at a time, not one atom, one element at a time, atomic emission can measure many, many different elements all at once. So it has a detection limit that's typically much better than flame atomic absorption, but not as good as other types of atomic absorption. So they're sort of in the middle. And then at the top, in terms of sensitivity, is atomic mass spectrometry, where you are doing much the same process, taking a liquid sample, generating ultimately free atoms. But in that case, you are, in mass spectrometry, most mass spectrometers utilize a magnetic field to essentially select, so rather than have a monochromator or something that selects what elements or wavelengths the lights get measured, they use a magnetic field to essentially select which ionized atoms will strike the detector. Okay? And they have much, much higher, better detection limits down to the subparts per trillion range in some cases. We'll see all this. Okay, so in all these cases, you could look and say, well, there's a relationship between detection limit and price, right? Just like cars, speed and price for cars. Well, for here, a flame AA like the one in the lab is probably about $35,000, not too much. To do a more sensitive kind of AA that we'll talk about, there may be $100,000. Atomic emission spectrometer is about $100,000, and mass specs go anywhere from $150,000 to $500,000. So the greater the sensitivity that you need, usually the higher the technology it's needed to drive that, and usually that costs a lot more. And for that reason, and a lot of students do this, you come and say, I want to measure levels of lead in soil. The levels I expect are, when I finally process the soil and get a liquid leachate, are going to be 5 micrograms per mil. And I just saw this cool demo by Rob Franks with a mass spectrometer that could measure it down to 0.01 parts per trillion. And I want to use that. And I'd be like, that is really silly, because if you have levels that are in the microgram per mil range, why would you use an instrument that can measure so much more sensitive? You got to dilute your sample down so much to get the working range that you're wasting your time. Why not use an instrument that's much simpler and faster, totally appropriate? Like, all right, and it's positive, let's go do that. So the way the instrument works that you're going to use, can be broken down into these very simple components like we've seen, some of them like we've seen before. And I want to say this now, and I'll reiterate it many times. With atomic absorption, or any kind of an atomic measurement method where we're measuring atoms, the atoms that we're measuring, whether it be absorption of light that we're passing through the sample of those atoms, or emission due to photons that are being generated from these atoms after they've been excited, or the
the mass of these atoms if they strike a detector and a mass spectrometer. In all cases, these atoms have to be free. And what do I mean by that?
Not a liquid?
Okay, even more than that, what else do I mean by that?
Not interacting with other atoms.
It means totally atoms free within some matrix, typically some aqueous matrix, right? They cannot be complexed with other atoms. They cannot be as part of some molecular species. All those things, they cannot be coordinated or bonded to something else. All those things will affect the energy that it takes to excite the atom if it's atomic absorption, or the energy that it takes to excite and then generate an emission photon, or the energy it takes to generate the atom so that it becomes an ion, so it can be traveling down a negative field in the process, steered to the detector. So all atomic spectroscopy methods require that the elements you're measuring be processed through some way, the instrument, into a free atom state. Okay? And so much of what these different spectrometers do, in terms of the front end, we call it, is in doing that, is generating these free atoms. So in the case of atomic absorption spectrometry, here's sort of a layout of what it looks like if it's a flame A, like you're going to use. And the basic components are, you start, because you're looking at absorption. And if you are doing an absorption method, what do you have to start with at the very beginning of this instrument?
Yeah.
What? In the UV vis, what's it start with? What do you start with at the very beginning of that method?
The light.
You start with light. You have to start with a source of electromagnetic radiation, right? Because you are measuring absorbance of that electromagnetic radiation. So you have to have a source of light. And the source of light used in atomic absorption methodologies most commonly is a lamp that's referred to as a hollow cathode lamp, right? And they're abbreviated HCl. And I'll talk about those in detail. So we have a hollow cathode lamp, and in atomic absorption, there's a specific lamp for every different element. So if you're going to measure 20 different elements, you have 20 different lamps at about $500 a pop. Okay? And I'll talk about that. So the hollow cathode lamp is generating electromagnetic radiation spectra that's specific to your element. So if I want to measure copper, I put it in a copper lamp, and it generates a spectra of light. And I'll talk about how it works. It's specific for copper. Okay? And that helps the selectivity. Then that selected light passes through my sample, which has been sucked up into this instrument and turned into a mist and air, and then that mist introduced into a hot flame, air-settling flame in your case. And now the heat in that flame then causes the atoms in that mist to evaporate, desolvate, to break apart if they're molecular species, and generate a gaseous state of the free atoms. And they travel through that flame for maybe, I don't know, half a second or so. So you're constantly aspirating your sample, it's being sucked up and processed in that flame, and the light is passing through that flame, and it interacts with your sample. So like the spectrum of light.
Is that similar to GC, the gas chromatography?
It's similar in the sense that you have your analytes are in the volatilized in the gaseous state. That's about the only similarity. So the light passes through there, then of course it goes through a monochromator to filter out the light for the wavelengths you really care about. We'll talk about that. And then they get detected, right? So in all these cases, we look at this light source that generates a very specific spectra of light that's specific to the analyte we measure. We have to process our liquid sample, so we take the atoms in that sample that may be complex with things, and we put them into a free atom gaseous state. In this case, in your case, you'll see, I'll talk about this, you're going to have a burner, and it literally is a burner, that looks almost about that size. And if I were looking down from the top, so we'll have our light source like this, going across like that. And if I were to look down from the top of the burner, it looks about like this, and there's a slot right in that burner end that's about a millimeter or half a millimeter wide. And there's a bunch of plumbing down here, and our sample gets introduced into the burner with gas sort of sucking it in with the Venturi effect, and it gets aerosolized in this nebulizing chamber that we'll talk about, and it gets put into a mist, very, very fine droplet mist up into the flame here. And the heat from that flame, then the samples constantly pass up and away. And about maybe 1% of the liquid you introduce into the instrument makes it up here, and the rest of it drains away into a drain. And as the sample is passing through that light path that's going through, then it interacts with those photons. And the copper, in your case of say, or lead, or whatever it is you're measuring, the copper or lead atoms that are in here will interact with the spectra of light that's here, and if the energy of that light matches the energy required to excite the electrons in that atom to a higher energy level, they will absorb that photon. And we are measuring the intensity of light entering, essentially, versus the intensity of light exiting. And the difference, just like in UV spectroscopy, is how much of it is absorbed here in the sample film. Okay, so we'll do all that. Right now, of the three kinds of methods we sort of just have mentioned, the process is this. We're going to be doing atomic absorption. In atomic absorption, we have radiation that's going to excite electrons to lower their ground state energy level. And if the energy associated with the photon that we're interrogating the atom with matches exactly the energy, quantum energy required to excite that electron to excite an orbital, it'll absorb that incident photon, right? And then it'll be lost. And when that electron falls back down to ground state, it will emit a photon of a different energy wavelength that we don't even care about, right? So all we're measuring is how much of that excitation radiation is absorbed by the atoms that are sampling. In atomic emission spectroscopy, we are not using light to excite things, but we're using a really hot gaseous plasma typically. And that plasma environment causes all the atoms in there to get so hot they slam into each other, not so hot, but they're energized, if they're moving and vibrating, and slam into each other. And that collisional energy is what results in the excitation of electrons to a higher energy level. And then when they decay back down to the ground state, they emit a characteristic photon that's characteristic of that energy drop. And that's what we measure for atomic emission. And then in fluorescence, it's essentially the same process where we excite it with an emission, with an excitation wavelength. And what we're measuring is the emitted wavelength, the photon characteristic wavelength. We'll talk about fluorescence spectroscopy a little bit as well. Okay. So, to reiterate the point I made a little bit before, you can get periodic tables like this off the web that break down for each element the approximate detection levels for different analytical methods for measuring those elements. And so in this case, he said, I'm going to measure copper and lead. That's what you're going to do for lab 3. And you can look across and see how the detection limits vary based on the kind of instrumentation that's being used. Now, of course, since there's a relationship between cost and detection limit, and we're a public institution, we have a relatively inexpensive instrument that's totally adequate for some things, but would not be adequate for other things in terms of detection limits for measuring copper or lead or those things. And you can look across and see that, if we're looking, for example, for flame atomic absorption, which is the second number down, so it's about 10 mic. That's probably an overestimate. That's probably better than what you might actually get in the lab. So that would be 0.01 micrograms per mil detection limit from the flame A in our lab. It's probably a little better than what you might get. So for lead, it's 10. You look up for copper, it's, what is it, 0.02, right? Am I looking at the right number? 1, 2, 1. Sorry, second number, 1. So copper is about 10 times more sensitive on the flame AA than is lead, which is true, right? It's actually pretty good for measuring copper. Okay? So the detection limits vary substantially by element, right? There's almost 100-fold higher for nickel. Right? And so there's reasons for that. We'll talk about why the detection limits might vary from one atom to the next. And it really is based on the electron configuration of the atom. Okay, so this is a cartoon I was showing you a few minutes ago. So we start with a source of electromagnetic radiation for atomic absorption, and there's actually two common sources that are used in instruments. One is a hollow cathode lamp that I'll talk about in a second. And the other one's called an electrode-less discharge lamp. I won't talk much about those because they're mostly used in graphite furnace absorption. So this is the source of light that matters, and these are very sophisticated compared to the D2 lamp that we've seen in UV-Vis. The sample introduction processing front-end compartment in a flame, it's very simple, just a hot flame, right? Air acetylene flame that is processing their sample from the liquid up into the gaseous atomized state. But there's other ways to do that are actually far more sensitive. And one example is a graphite furnace where it's a small tube about the size of this piece of chalk, where your sample is injected into with an auto-sampler, about 20 microliters of sample, and then it goes through a program to heat that tube up, you know, to 100 degrees for maybe a minute, and then do 500 degrees to break any organics, and then up to 2,000 or 3,000 degrees, depending on what element, to volatilize and atomize the sample in this space, but it's a hollow tube. And then the light's passing through that tube, and it sits there for 3 or 4 seconds, so it has a long residence time, unlike the flame. So it has a much higher detection limit. And for all kinds of absorption methodologies, there is one component that is essential. And we talked about this to some extent with the UV-Vis spectrometer, and these are also very important in functionality and atomic absorption spectrometers, because we need to be able to select and measure one particular wavelength, not a whole bunch of wavelengths. And so the monochromator is essential for allowing us to do that. Okay, so I meant to bring in a lamp. I'll bring one in on Wednesday. You'll see it in the lab on Monday. So these things are about, you know, typically they're about that big, right? This one's shaped a little bit different, but they're bulbs about that big that have, you know, the wire coming out with a plug on the end of it, it plugs into the instrument. And they're all constructed looking something like this, that they're sealed off, for one, so they're a sealed, essentially, lamp. At the end of the lamp is a quartz window, because quartz is more transparent to light across a broader range of wavelengths. There's one very important fact that I want to say for you when you handle these lamps, is to don't put your grubby fingers on the quartz window, because your oils from your fingers cause that to get a little etching. They'll put etches in there over time, and those etches or scratches will cause the light that's being passed out to get reflected and diffracted at different angles, which is suboptimal. Right? So this will be clean, and you won't touch this with your fingers, but you can touch the glass with your fingers, because the light's going out that way. Right? And so these lamps are sort of a relatively ingenious design when they first came out decades ago. And they call them a hollow cathode lamp because they exactly have a hollow cathode. They're fitted to have cathode and anode. And the cathode is composed of the metal that you are going to measure. This lamp is for. So if you're going to measure copper, this is a copper hollow cathode lamp. The cathode here, which is like a hollow tube about that long, maybe as big around as this chalk, on this hollow, and it's made out of copper, pure copper. If you're going to measure lead, you put the lead lamp in, this hollow cathode will be made out of lead. Right? So for every element you're measuring, the lamp is specific to that element because the cathode is made out of that element. And the way these things work is quite ingenious, is that you plug it in and you apply a current to the lamp, maybe 10 milliamps or whatever, it varies from one lamp to the other. And that current you apply across the anode and the cathode, one point I forgot to say is the lamp is filled with a low pressure of an inert gas, typically argon. So it has an inert gas, no oxygen in there, at higher than atmospheric pressure. When you plug it in and turn the current on, it puts a current potential between the anode and the cathode. And then what happens is that the argon atoms that are in there, in the current, then get ionized. And those argon atoms get ionized into an ion, and they sort of generate a very localized plasma of hot argon ionized gas in that space. Now those positive argon ions that are just here between the anode and the cathode then get attracted to and accelerate towards the cathode, because this is negative. They accelerated, and those argon ions hit this cathode in the middle here in this hollow tube, of the cathode, and they hit with such velocity that they sputter off a little bit of the metal, atoms of the metal, in this case, the copper. So they're sputtering off copper atoms from this solid copper cathode into this hot gas plasma, and those copper atoms get excited because it's really hot, and when they get excited, the electrons get excited to a higher energy level, and then when those copper atoms reach a slightly cooler place in here, where they're not colliding with other argon or copper atoms, those highly excited electrons fall back in their ground state. And what happens when that happens?
Battery. Battery should come on.
I think you said, but I see you said they emit a photon of characteristic wavelength. Is that what you said? Yes, that's true. Right. They emit photons of characteristic wavelengths that match that, essentially that decay energy when those electrons fall down to the ground state electrons, right? And that spectra of what they release is specific to copper, right? That's how we generate. And so the advantage of a hollow cathode lamp, as opposed to what we used in UV vis spectroscopy, which was a deuterium arc lamp, right, is that the hollow cathode lamps, with a specific cathode element, cathode, generate a very specific spectra for that element. Okay? And that's very important in atomic absorption. We'll talk about why that is. So this just says what I just said, so I'm not going to belabor it. And I'll post this on the website. But the bottom line is that when we create these argon atoms, they're ionized because of the potential across the atom of the cathode. They strike the metal of the cathode, and you get this sputtered off metal that gets excited and it decays to the ground state. And excited to the ground state, you release photons of characteristic wavelengths of energy. Right? And that's what we care about for atomic absorption. And so if you look at some typical atomic absorption, or these are wavelengths of light that are being emitted by the hollow cathode lamp, not being absorbed by anybody yet, right? These are being emitted by the hollow cathode lamp. You can see how specific and sharp they are. For some elements like calcium, the spectra are very simple. And for other elements, in this example, nickel, the spectra, the atomic spectra of emitted photons is more complex. But there's one thing that's really interesting and important here, and that is if you look at the resolution of this spectra compared to what you saw in UV vis spectroscopy, these are extremely sharp atomic lines of spectra that are being emitted by these lamps, right? That differ by sometimes 0.005 nanometers. So the resolution of that spectra is extremely fine. And remember, one of the advantages or the necessities in all these absorption methods is we have to be able to select a very specific wavelength of light with which to interrogate our sample, right? Because they absorb light at very specific energies or wavelengths. And so the more successful we are generating a spectra of very sharply defined wavelengths, the more successful we'll be at being able to interrogate our sample with a particular wavelength and measure the absorption that's very specific to just that wavelength and just that one atom. Okay? And that's the advantage of atomic absorption. This is, you may recall, is what the emission spectra look like for a deuterium arc lamp. So this is the emission spectra of copper atoms that have been excited, okay? Going from 234 to 230. So these are just 4 nanometers in difference, right? So it's like there, and you can see how much more specific and sharp this is. Of course, the scale's different, but compared to what you can get from a deuterium arc, it's a very broad band emission spectrum. These are really cheap, $50. These are like $300 to $400, $500. And you can get away with that in molecular absorption because the absorption bands are broad. But you can't get away with that in atomic absorption because the atomic absorption bands are very, very thin.
I just had a question about the hollow cathode design. Does that, since the argon or whatever's in there is actually like striking and getting one atom off of it, does it degrade over time?
Does what degrade?
The cathodes.
Yes. Yes. So they have lifespans because over time you are depleting the cathode surface. Yes, that's correct. Right. They have a long lifespan, but still they have a lifespan. Like a lens. Okay. Okay, I'll talk quickly about how we get our samples. So if you were to sort of itemize what matters in atomic absorption, one is what matters. One is a very specific light source. That won't be relevant to say. Another is sample from a liquid to gas atoms. Right? So we have to have a way to do that. It's efficient. So the way it's done in flame atomic absorption, which is very inefficient, is that there's a nebulizing body that's fitted at the end with the burner head where the gases come out there into a flame. And you'll see this in the instrument on Monday or Tuesday. And this looks just like the one that you'll be using for the most part. Is you have a little capillary tube coming out of here that has an inner diameter of maybe, a tenth of a millimeter or something like that. And so it'll be important you don't have any floaty stuff in your samples because that'll clog that. And then you have your gas mixture, which is the fuel, which in your case will be acetylene, we'll use welding, and the oxidant will just be air. So it'll be an air acetylene flame. And on the instrument, we'll set the mixture of those two gases so that we have a nice hot flame, but not a really smoky flame or not something that's going to blow up. Okay? And that mixture of gas will come in here, and the gases then come in, the air, oxygen, gas comes in and flows along this, and your tube comes in. This is a really small diameter tube with an outer jacket, and the Venturi effect of the gas flowing through here, then it will start to draw your sample just by flow, not gravity, but by a Venturi effect of the air pushing along this way across the tip. Will create a force to suck your sample up at a relatively constant flow rate of maybe, a milliliter a minute or something. That liquid sample comes in with this rushing gas, and in this example, hits this glass bead that's hanging down, and that impaction then takes that liquid spray that hits that bead and sort of creates these more aerosol droplets. And then the gas is flowing around in here, it goes through these baffles, and spinning around, and what that does is it essentially selects for the very fine, small diameter droplets, like, tens of microns at most. It'll be carried up into the rushing gas. All the bigger drops will fall down to the bottom and just drain out. This is where 99% of your sample will go. And 1% of it will be in those fine droplets in the air and end up getting introduced in the flame. And you got essentially a little lighter up there that will light the flame for you automatically, right?
Can you reuse the drain stuff, or is that just?
It just goes away.
Okay.
You don't dispose of it properly. And the TAs will warn you, and I'll warn you now, like all really bright flames, they emit really high levels of ultraviolet radiation. And so even though the flame's really pretty, you don't want to sit and look at it directly because it's good. But people, sometimes it's hard to, right? But you start analyzing different samples, the color of the flame will change because you're seeing the emission of the spectra of different anything in your sample, right? But you want to look at that. And then that sample passes up there, and it passes through that flame, and then your light beam, like I said before, is coming parallel to the burner flame, the burner head, and it's only there for less than a fraction of a second. And so you're constantly aspirating sample while you're making the measurements of absorbance. And then as soon as you make those measurements, and the absorbance measurements take, you might set your program up to take, 5 or 10 measurements and integrate the measurement over half a second or 0.2 seconds. So it may only take you 2 or 3 or 4 seconds to make the measurement, but you'll be aspirating stuff up for maybe 15, 20 seconds. So the measurement time is really fast, unlike when you just finish with chromatography. You can make 10 measurements in 10 minutes. So it's really fast.
How much sample do you actually enter in the?
You'll find out. So typically you say I've got, if it's aspirating at maybe a maybe it's a couple mils a minute, depending on how you set it, then you probably would want to start with at least it's 5 mils, and if you need to remeasure it because it didn't look right, usually you want to come in with something like 10 mils of sample. All right, so I'm going to stop now because I want to, we'll talk more about this on next Wednesday. I want to kind of switch gears a tiny bit, and now I got to switch this so you can see that one. So what I'm going to do now, I'm going to quickly go over some things. Is everybody going to be able to come by after class to talk about lab stuff, or no? Okay. So I'll spend a few seconds on this, and then we'll do a quiz.
Well, you wrote about the 12:30 to 1:30.
Is that what I said? Okay.
Is it going to be at full time?
Yeah, unless, I mean, if people there at 12 until 1, and there's somebody else there, I'll just go back to my office. That's just right across the hall. So, I want to reiterate a few things here. 5 minutes with this. So this is something you've seen many, many times. And we're now into lab report 2, sorry, lab report 2. And I want to underscore some things. One is this text for describing how to use and set up tables and figures. Some people are still having a little bit of a hard time with that. Please go and read this carefully. Figure captions go at the bottom of a figure. Table captions go at the top of the table. The captions should be complete and allow the reader to understand what is in the table or figure without having to read the text of the report. Right? That's standard. So read this carefully. I also talked about what kind of information you put in a table versus a figure, because there's a prioritization that the most important stuff graphically would go through the figure.
Is this the paper you handed out to us?
It's on the website, I hand it out to you, it's the same thing. Now, this is where we're starting now, the full lab report, right? So one thing I want to say is, and we didn't sort of enforce this so stringently for the first lab report, but we will for the second one, is that no more than 7 pages of text. Okay? If you have more than 7 pages of text, we will not grade it. Okay, we'll send that back to you. So, and that's single-spaced. And that's because you may say, oh, I want, some people have this mindset that more is better. And in cases like this, more is not better, more is worse. Because the more words you use, typically the less clear something is. Right? And so I have an exact format that I'd like you to follow, and I give you sort of a recommendation for how long to make those, right? If it's less than 7 pages, that's totally cool. If it's 3 pages, that's not, right? If it's like 5 to 7, that's, if you were to bunch them all up and not have them on 7 pages, that's okay, but it should be no more than 7 pages of text, and certainly I would expect probably no fewer than 5, if possible. So you'll follow this really closely. And I tell you here not only what order. So page 1 would be obvious what's there with an abstract, right? And people written an abstract before? So you know that an abstract typically is the last thing you write. Some people think, oh, it comes first, so let's write it first. The abstract's the last thing you write, because the abstract is going to capture every element of what's in the report, right? It's going to capture what your objective was, why you think it's important to do it, the rationale, how you did it, what you found, what do you think it means, right? And so you'll put all these things in the abstract, like I answered, but I recommend you do that last. When you start writing the introduction and the background, 1 page maximum, these are the things that I'm suggesting you consider. This is just a suggestion, about 1 paragraph to do this, a couple paragraphs on this, 1 final paragraph saying, this is what I did, this is why. Okay. That's just my suggestion.
Do you want to set the checklist again like we did last time?
Yes.
That one is right up there.
Yes. And this is like, what do you do, as a writing instruction, what are you trying to do in the introduction or the background? And the idea is, which is sometimes hard to balance when you're trying to just get the thing written, but the idea is to think like, I am writing a story that I want to make somebody want to read. And so the introduction is that part where you are trying to sort of create the compelling nature of why this is being done, why it's important. And so when the reader reads that, they're going to gain enough understanding about what the background is, why it's important, so they're convinced that what you did is probably worth reading about. That's the overall goal of the introduction. In your case, which is different from lab, the first lab, is I want you to spend a couple of paragraphs talking about the theoretical basis for the instrumentation, for the methodology that you use, or why it works, right? Not just about why you want to measure these anions in some samples. So I go through here, and I'm not going to go through all this in more detail now, but I go through here and I provide, I think, a lot of information that I think you should pay close attention to because it will help you with the document. So if you print this out and you have it next to when you're starting to write, go through and check off the things that you want to make sure you include, right? So that you have all the elements there. Then outline those elements so that the information's there and organized the way you want. Then go back and say, how can I now put the text here to explain things in a way that will be clear to understand and easy to follow by the reader. And many of you have gotten comments from us about writing things in the report that we may understand what you mean. Right? And a common challenge for writers who are writing things like this is that I thought a lot about this, I know all about this, and so this is obvious to me, and they don't realize that it may not be obvious to the reader. So the issue is specific. Okay, I'm not going to go into more about this. I think that's not right. Okay, so we'll talk more about this when people come by if they want. So let's do a quiz.